All right, today we are diving headfirst into the most violent, most energetic events in the entire universe. We're talking about a fire hose of cosmic data from exploding stars and, those supermassive black holes. And the really cool part? The brilliant AI that's finally letting us make sense of it all. So our story really kicks off with just one number, 2 million. Get this, that's how many cosmic X-ray sources our telescopes have already spotted out there. And these aren't just any old dots in the sky. No, we're talking about the brightest, most violent objects imaginable. Things like supermassive black holes, literally devouring stars, collapsed stellar remnants, called neutron stars, and flares so massive they'd make our own sun look like a tiny flickering candle. And that brings us to one of the biggest challenges in astronomy today. It's a bit of a paradox, really. We're not limited by what we can see anymore. We're limited by what we can actually find. I mean, how on earth do you spot that one single textbook rewriting discovery when it's buried in a sea of 2 million signals? How do you find that needle in a galactic haystack?
Because that is exactly what we're dealing with, a galactic haystack. Yep, X-ray astronomy has officially entered the era of big data. Every single day, telescopes like Chandra are beaming down a literal tsunami of information. I mean, it is so much data that it is physically impossible for any human or even a team of humans to keep up. So we need automated systems. We need them to process and analyze all this stuff, not just to manage the flood, but to actually make discoveries on a scale we've never seen before.
But here's the catch, and it's a big one. Analyzing X-ray data, it's not at all like looking at a beautiful, crisp picture from Hubble. There's this fundamental weirdness to it that makes it incredibly tricky to work with. Okay, think about it like this. A normal photo, right, that's made of millions of photons hitting a camera sensor pretty much all at once. We call that high-count data. But a really faint X-ray source, well, it might only send a handful of photons our way over several hours. The arrival of each one is sparse, it's random. It's much more like hearing individual raindrops hitting a tin roof, then seeing a steady downpour.
And this kind of randomness, it actually has a name. It's called a Poisson process. And this is the key statistical rule that governs all of this data. What it really means is that every single photon that hits our detector is a completely independent event. And you have to understand this. It is absolutely crucial. Because if your method for analyzing the data ignores this fundamental randomness, you are basically guaranteed to get the wrong answer.
So, for decades, the standard way to deal with this was a technique called binning. Let's go back to that rainstorm analogy. Imagine you want to measure how hard it's raining. You could put out a whole row of buckets, and at the end of every minute, you check how much water is in each one. Well, that's pretty much what binning does with X-ray data. It just chops up the observation time into these fixed-sized buckets and counts how many photons happen to fall into each one. And this really shows you the problem perfectly. On the one hand, you have the raw, actual arrival of photons, the real signal. Then you force those events into these artificial time bins, and what do you get? A blocky, distorted, kind of mangled signal that has lost a ton of crucial information. A super fast flare that happened in just 1 second, it might get smeared out over a 10-second bin, completely hiding it. And for those really faint sources, you just end up with a bunch of empty buckets and noise. You've essentially broken the data before you even start your analysis.
So clearly, the old way is fundamentally broken. It just doesn't work for this kind of data. We need a totally new way to see. And this is the breakthrough. A solution that was designed from the ground up to respect the data for what it actually is.
So what if we could just get rid of the buckets altogether? What if we could develop a tool to see the storm itself, not just the water collected in some arbitrary containers?
Well, let me introduce you to PPAD. That stands for Poisson Process Autodecoder. It's a brand new AI model that was purpose-built for this exact challenge. And its secret weapon? It works directly with the raw event files, that pure, untouched list of photon arrival times. It completely bypasses that entire flawed process of binning.
And this comparison right here really shows you what a game changer this is. I mean, let's just go through it. First, the statistical model. The old methods, they make assumptions that just don't fit the data. But PPAD, it's built on that Poisson model we talked about, so it respects the true random nature of what's going on. Then there's data input. The old way needs those clunky, compromised bins. PPAD just takes the pure, raw events. And maybe the most important part is the final result. The old way gives you this blocky, low-resolution guess. PPAD, on the other hand, gives you a continuous, what they call resolution-free, reconstruction of the cosmic event as it actually happened.
But honestly, it gets even better. PPA does something even more powerful than just reconstructing a signal. It actually learns to understand the data on a much, much deeper level. It learns to see the very essence of a source, what you could call its unique cosmic fingerprint.
And it pulls this off using a really clever AI architecture called an autodecoder. Now, the key thing to know is that it does two incredibly powerful things at the exact same time. First, it learns to perfectly reconstruct the original signal, and second, it learns how to create a really meaningful compressed summary of that signal. So, as PPAD is churning through that raw photon data, it produces two things. The first output is that beautiful high-resolution light curve we talked about, basically a perfect picture of what the source was doing over time. But then there's the second output, this compact little string of numbers. It's called a latent vector. And this vector is a really dense, abstract summary of all the source's most important features, all rolled into one. This latent vector, that's the magic key. That is the unique cosmic fingerprint. And here's the crucial difference from the old way of doing things. Instead of an astronomer having to manually decide which features to look for, which, can be slow and full of human bias, PPAD learns the most essential characteristics automatically just by looking at the raw data. It's a totally unbiased, data-driven way to describe what makes any given source unique. And that brings us to the ultimate payoff. Because once you have an unbiased fingerprint for every single source in your massive catalog, you can start doing something truly incredible. You can go hunting for hidden twins. Okay, so let's put this thing to the test. The researchers who developed PPAD picked a specific source. It was something they knew was interesting, but also notoriously difficult to analyze. A very dim flare that emits mostly high energy, or what astronomers call hard, X-rays. This thing was a classic needle in the haystack. So here's the million-dollar question. Can we take the unique fingerprint from this one tiny, faint flare and use it to search through the entire catalog of hundreds of thousands of other sources to find its twins? To find other objects that behave in the exact same way? The answer? An absolutely resounding yes. I mean, PPAD didn't just find one or two maybes. The researchers looked at the 15 closest neighbors to their target source in this abstract fingerprint space, and get this, almost all of them were the exact same type of object. They were all other low-count hard-band flares. The system worked. It worked perfectly. And you have to realize, this is so much bigger than just finding a few matches. This demonstrates an entirely new method for systematic discovery. It means you can find one weird, interesting object, generate its fingerprint, and then instantly find its entire family, even if they were completely buried in the noise and totally impossible to spot before. Which, brings us right back to where we started. By using this AI to learn the fundamental essence of these cosmic signals, to learn their fingerprints, we finally have a tool that's powerful enough to search for needles in that galactic haystack, and to actually, finally, find them. And look, this technology is really just getting started. Which leaves us with a pretty thrilling final thought, right? Now that we have a reliable way to find these hidden cosmic twins, what completely new, undiscovered families of objects are out there, just waiting for us, hiding in plain sight in the data we've already collected?